Series of positive terms, tests of convergence or divergence. This is a continuation of the first video where we learn about the comparison test. Here we are going to study about the second test, which is the Cauchy's root test. So first, we will see what the statement is. The statement is let summation n equals to 1 to infinity an be a series of positive terms and let p equals to limit n tends to infinity n root of an. Then first, if p is less than 1, then the series summation n equals to 1 to infinity an converges. Secondly, if p is greater than 1, then the series n equals to 1 to infinity an diverges. But thirdly, if p equals to 1, then this test does not give a definite conclusion. Which means that the test fails. We will understand this better if we take a look at some applications of this test. Now for the first example, we need to investigate whether the given series converges, which is 1 by 3 plus 2 by 5 whole square plus 3 by 7 whole cube plus till n by 2n plus 1 to the power n, and this goes on. So the given series is summation of an, where an equals to n by 2n plus 1 to the power of n. Now an to the power 1 by n equals to n by 2n plus 1, and this tends to half as n tends to infinity. So we all know that half is less than 1. Therefore, we can conclude that the given series an converges by Cauchy's root test. For our second example, example number 2, we need to investigate the given series, which is 1 plus 1 by 2 cube plus 1 by 2 square plus 1 by 2 to the power 5 plus 1 by 2 to the power 4 Okay, so for the solution, first we need to know what an is. So this is a given series an where an equals to 1 by 2 to the power n plus minus 1 to the power n. So an to the power of 1 by n equals to 1 by 2 to the power 1 plus minus 1 to the power n by n. Therefore, we can say that an to the power 1 by n tends to half as n tends to infinity. So this limit exists and the limit is less than 1. So by Cauchy's root test, the given series is convergent. Here our second test ends. So after the comparison test and Cauchy root test, there will be a series of tests known as the ratio tests. Under this, we have 3 tests. The first one is Allembert's ratio test. It states let summation n equals to 1 to infinity be a series of positive terms for which limit n tends to infinity an by an plus 1 exists and is equal to, say, L. Then there are 3 conditions. The first one is the series an converges if L is greater than 1. The second one is the series an diverges if L is less than 1. And the third one is the series an may or may not converge if L equals to 1, which means that the test fails. In that case, we need to head to the second test, which is the Rabi's test. So under ratio tests, Rabi's test is the second test. This states let summation an be a series of positive terms, because we are dealing with series of positive terms, and let limit n tends to infinity n into an by an plus 1 minus 1 exists and equals to L, just like the previous one. So here also we are given 3 conditions. The first one is the series an converges if L is greater than 1. Second one is the series an diverges if L is less than 1. And the third condition is, just like the previous case, we come to no definite conclusion if L equals to 1. So the Rabi's test is certainly applicable if D'Alembert's test is applicable, but the Rabi's test may give a definite conclusion even if D'Alembert's test fails. So we may say that Rabi's test is stronger than D'Alembert's test. But in the case where Rabi's test also fails, we may try the third test, which is Demorgan and Bertrand's test. Number C, Demorgan and Bertrand's test. Its statement is, let summation an be a series of positive terms and let Bn equals to log n within brackets Rn minus 1. Now Rn equals to n into an by an plus 1 minus 1, which we took in the Rabi's test. Now this equals to n an by an plus 1 minus 1 minus 1 within brackets, then log n. Then the first condition is the series an converges if limit bn is greater than 1 and the limit an diverges if limit bn is less than 1. So these are the three ratio tests which we may apply in our example, which is, we are given a series and we need to investigate the convergence of it. The series is 1 square by 2 square plus 1 square into 3 square by 2 square into 4 square plus 1 square into 3 square into 5 square by into x, 2 square into 4 square into 6 square into x square, plus this goes on till 1 square into 3 square into 5 square till 2n minus 1 whole square by 2 square into 4 square into 6 square till 2n whole square into x to the power n minus 1. This continues where x is greater than 0. So now we notice that the numerator are odd numbers and the denominator are even numbers. Using this series, we will test the convergence of it by using all the three ratio tests. So now for the solution, let the series be summation an where an equals to 1 square into 3 square into 5 square till 2n minus 1 whole square by 2 square into 4 square into 6 square till 2n square into x to the power n minus 1. Now since we know that x is greater than 0, each term of the series is positive. That is, summation an is a positive series. Now, an by an plus 1 equals to 1 square into 3 square into 5 square till 2n minus 1 whole square by 2 square into 4 square into 6 square till 2n square into x n minus 1. This is multiplied by 2 square into 4 square into 6 square till 2n square to n plus 2 whole square by 1 square, 3 square, 5 square till 2n minus 1 whole square, 2n plus 1 whole square into 1 by x to the power of n. Now solving this, we get 2n plus 2 whole square by 2n plus 1 whole square into 1 by x. Therefore, limit n tends to infinity, an by an plus 1 equals to limit n tends to infinity 1 plus 1 by n whole square by 1 plus 1 by 2n whole square into 1 by x, which equals to 1 by x. Therefore, by D'Alembert's ratio test, the series an converges if 1 by x is greater than 1, that is, if x is less than 1, or we may say if 0 less than x less than 1, since x is greater than 0, which is already given, and the series diverges if 1 by x is less than 1, that is, if x is greater than 1, and no definite conclusion should be drawn if x equals to 1. No definite conclusion for x equals to 1. So when x equals to 1, we need to go to the next step, which is the Rabi's test. Now for the Rabi's test, we need to find Rn, which equals to n into an by an plus 1 minus 1. This gives us n into 2n plus 2 by 2n plus 1 whole square minus 1, which equals to n into 4n plus 3 by 2n plus 1 whole square. Now limit n tends to infinity, Rn equals to limit n tends to infinity 4n square plus 3n by 2n plus 1 whole square. This equals to limit n tends to infinity 4 plus 3 by n by 2 plus 1 by n whole square. Now this gives us 1. So, therefore, Rabi's test also does not lead to any definite conclusion. of the given series when x equals to 1. Therefore, we need to head to the third step, which is Demorgan and Bertrand's test. For this, we need to find Bn, which equals to log n into Rn minus 1 equals to 4n square plus 3n by 2n plus 1 whole square minus 1 into log n. This gives us log n by n into minus n plus 1 into n by 2n plus 1 whole square, which equals to log n by n minus 1 plus 1 by n by 2 plus 1 by n whole square. Therefore, limit n tends to infinity, Bn equals to 0 into minus 1 by 4, which equals to 0. Since log n by n tends to 0 as n tends to infinity. Thus, limit n tends to infinity, Bn exists and is less than 1. Hence, by Demorgan and Bertrand's test, the given series, which is summation an, diverges for x equals to 1. So this is the conclusion, that the given series summation an converges. We conclude that the series an converges if 0 less than x less than 1 and diverges if x is greater than equals to 1. So in this way the ratio test is done. For the first test, which is the comparison test, please check the first video.